Hello everyone, this is Sheila Ratna Bansode from Walchand Institute of Technology, Solapur. Today we are going to see the topic minimum starting speed and net positive suction head in case of centrifugal pumps. Let us move further. At the end of this session, students will be able to, the first learning outcome is to discuss minimum running speed, that is minimum starting speed. Then to discuss net positive suction head, that is NPSH. Now before moving on further, I suggest you to pause the video and recall the construction and working of a centrifugal pump. And also the details, the parts of centrifugal pump. Let us move further. Now, whenever we are using a pump, a centrifugal pump rather, we require the minimum threshold pressure or the speed to be reached so that the fluid or water from the desired source can be lifted or can be supplied to the destination. Now, there's an addition what we can say. Instead of saying minimum starting speed, let us call it as minimum running speed, because this speed is required throughout the functioning. It's not that once the pump is started, then the speed can be changed. The same speed needs to be maintained. So instead of calling it starting speed, we say it as minimum running speed. If pump develops head more than manometric head, if the desired developed pressure is more than the manometric head, then delivery of liquid is possible. Unless and until the desired or developed head does not reach the manometric head or more than manometric head, the delivery of fluid is not possible. That is, a suction of fluid with the help of that centrifugal pump is not possible. Now, difference in kinetic head at outer and inner diameter of impeller is pressure head. Now we can say when the impeller is rotating, the kinetic head at the outer diameter and the kinetic head at inner diameter, this causes the pressure head to be developed. Now when we say we increase the pressure of a fluid, we mean that we add pressure energy to the liquid. When your impeller is rotating, slowly the pressure is built, but it is revolving at a high kinetic energy or high velocity, and that will try to accumulate for very small time at the delivery pipe, and then will have the desired pressure. But initially, as I mentioned, we add kinetic energy, and that kinetic energy is converted into your desired pressure energy. But it is different at different points on impeller. The kinetic energy at a point on the circumference of our impeller will be different as compared to the point at the center of the impeller. Moving further, see, as I mentioned, at inner diameter, kinetic energy is lesser. Now, kinetic energy at inner can be mentioned as U1 is equal to pi n d1 upon 60. Now, the outer diameter, the kinetic energy is more due to higher linear velocity. At the end of the impeller, the kinetic energy is more, which can be mentioned in the equation that U2 is equal to pi n d2 upon 60 as d is larger. Now the difference between these two kinetic energies is addition of kinetic energy. Now difference between these two helps to add kinetic energy to the fluid, that is building of pressure. So later on, the same converts into pressure energy. The difference in the kinetic energies causes the addition of kinetic energy to the fluid, and that same kinetic energy is converted into pressure energy. Now difference in kinetic head at outer and inner diameter of impeller is developed pressure head. So that is nothing but the developed pressure head. Moving further, so for discharge to occur, head due to pressure rise in impeller will be the difference of U2 square upon 2g minus U1 square upon 2g. So this subtraction should be greater than or equal to manometric head. But we know that efficiency of manometric efficiency is equal to acceleration of due to gravity into manometric head divided by velocity of whirl at the outlet and tangential velocity at the outlet. Now putting values of Hm in this above equation, we have u2 square upon 2g minus u1 square upon 2g, which is equal to manometric efficiency into Vw2 u2 upon g. We have substituted this value into equation 1. Now we know that velocity u2 is equal to pi dn upon 60. Similarly, u1 is equal to pi d1 n upon 60. Now substituting these values, we get 1 by 2g bracket pi d2 n upon 60 whole square minus 1 by 2g bracket pi d1 n upon 60 bracket square, which is equal to manometric efficiency into velocity of whirl at outlet plus pi d2 n upon g into 60. Now cancelling pi n upon g into 60 throughout, what we get is this equation. Simplifying further, we have minimum starting speed is n is equal to 120 into manometric efficiency into velocity of whirl at outlet into d2 upon pi bracket d2 square minus d1 square. So this is the minimum speed that is required to run a centrifugal pump or to have a proper suction and delivery of the fluid. Now moving further, net positive suction head. Now as far as net positive suction head or NPSH is concerned, it is a commonly used term in pump industry. So minimum suction conditions are more frequently specified in terms of NPSH. The minimum conditions, the minimum parameters that are required to have the desired suction and delivery of the fluid is specified with the help of NPSH. Now we can define NPSH as the absolute pressure head at the inlet of the pump minus the vapor pressure head plus the velocity head. Now let us move further. From this graph, we'll see this is the pressure versus discharge, you can say. Here, when at the start of the pump or at the suction, the pressure is more, that is atmospheric pressure. Then as the pressure goes on dropping till the I, and from I it will again start increasing. So this is the normal curve or the general curve that we have of pressure. Now this value is the vapor pressure. Vapor pressure is the pressure at which your fluid will start getting converted into vapors. Now if the pressure falls below this vapor pressure at the eye, the pressure at the eye is very low as compared to vapor pressure, then you will not have the desired functioning of the pump. There will be creation of bubbles, and these bubbles will try to escape in the fluid and burst at impeller, where the pressure will start rising at the discharge and will have a bad impact, a negative impact on the impeller blades. So the region above this vapor pressure, this region is called as the NPSH section or NPSH zone. So the pressure should not fall below this vapor pressure. Moving further, now NPSH, we know that P1 upon rho g plus Vs square upon 2g minus PV upon rho g. This can be reshuffled and written as PS upon rho g, that is pressure at section at this area. Then Vs square upon 2g, this is velocity, and minus PV upon rho g, this is potential. Now applying Bernoulli's theorem to this, what Bernoulli suggests is PA upon rho g, P atmospheric, plus VA upon 2g, VA square upon 2g minus ZA, this should be plus ZA, which is equal to PS upon rho g plus Vs square upon 2g plus Zs plus HFS. This is the losses during the flow. Moving further, PA upon rho g plus VA square upon 2g plus ZA, this is the corrected version, which is equal to PS upon rho g plus Vs square upon 2g plus Zs plus HFS. Now as far as at the section here we is concerned, the velocity can be neglected. It is very small. So neglecting that term, we have Ps upon rho g plus Vs square upon 2g is equal to Pa upon rho g plus Za minus Zs minus Hfs. Further, I'll take minus sign common. So Zs minus Za minus Hfx. So this is the equation that we have got. Further, we know that NPSH is this. Substituting this value of Ps upon rho g plus Vs square upon rho g, that is equation A, into this, we get Pa upon rho g minus Hs, that is suction, minus Hfs minus Pv upon rho g. Now here we got Hs because Zs minus Za here in the diagram, this is Za and this is Zs. So difference is Hs, suction, this. With this we can replace it by absolute head minus suction head minus loss head in losses minus vapor pressure head. So in order to have cavitation free operation, available NPSH should be greater than the required NPSH. References. Thank you.